Welcome to section 2.1, solution curves without a solution. Objective number 1, define a direction field for a differential equation. When solving differential equations, we may not always be able to find an exact solution. In these cases, direction fields provide a valuable way to analyze the behavior of solutions visually. A direction field or slope field is created by using the differential equation to plot a grid of vectors or arrows that represent the tangent lines to the solution curves at different points. These vectors are determined by plugging coordinates x, y into the differential equation, which gives the slope of the solution curve passing through each point. By plotting these tangent vectors, we create a flow map that helps us visualize the overall system and predict how a solution curve behaves as it passes through any given point x, y. There are two key reasons why direction fields are useful. Number one, sketching solutions. So the arrows in the directional field act as tangents to the actual solutions of the differential equation. So by following the flow of these arrows, we can sketch approximate graphs of the solution curves without solving the equation explicitly. And two, long-term behavior. So sometimes we're more interested in understanding how the solution behaves over time rather than finding the exact solution. So directional fields help us predict the long-term behavior of the solution as t increases, providing insight into trends like stability, growth, or decay. To illustrate, imagine we're working with a first-order differential equation of the form dy dx equals f xy. We are unable to solve it analytically. Even in this situation, the differential equation itself offers valuable information about the behavior of its solutions. By analyzing the differential field, we can get a qualitative understanding of the solution's curve shape and behavior without having to solve the equation directly. Objective 2. Interpret a direction field for a differential equation. So now let's walk through the process of analyzing the differential equation y prime equals x times 2 minus y using direction fields step by step. So step 1, identify the slope or tangent line at a few points. So the first step in creating a direction field is to calculate the slope of the tangent line at specific points by substituting the coordinates x, y into the differential equation. For the equation y prime equals x times 2 minus y, the slope y prime at any point is determined by multiplying the x coordinate by 2 minus y. So let's choose a few points and calculate the slope at each. So let's start off with the point 0, 2. So I'm going to take my y prime equals x times 2 minus y, and I'm going to substitute in my point 0, 2. So that would be 0 times 2 minus 2, which equals 0 times 0, which equals 0. So my slope equals 0. This means that the tangent line at this point is flat, it's horizontal. Now let's take the point 1, 1. So I'm going to substitute that into my DE. So that would be 1, 2 minus 1. So that's 1 times 1, which equals 1. So my slope here is 1. So this means the tangent line at this point has a slope of 1, indicating a 45-degree upward tilt. Let's look at two more. Taking my point and substituting it in, let's erase that, substituting it into my dE. So x is -1, y is 3, so -1 times -1 equals 1. So this is a slope of 1. So at the point -1, 3, we have a slope of 1, but in this case, it represents a 45-degree upward tilt at a point on the left side of the graph, because -1, 3 is a point on the left side of the y-axis, so we're going to have a 45-degree upward tilt on that side. Let's take our next point, y prime x times 2 minus y. Substitute in our point, -0, 2 times 2, which equals 4. So we have a slope of 4. Okay, so this is going to be a very steep slope because our slope here is 4. And our last point, -2, 2. So we'll take y prime x times 2 minus y, substitute in our x, substitute in our y, 2 times 0 equals 2. So our slope here is 2. So, sorry, not 2, 0. My apologies. Our slope here is 0. I think I added in my head instead of multiplied. All right, so the slope at this point, -2, 2, is 0. So just like at our other point, 0, 2, that we did first, this is going to indicate a horizontal line. Okay. So step 2 now would be to calculate the slopes at a few points, and we can plot those tangent lines on the graph. So we have our points that we did in step 1, so now we can plot their tangents on this graph. And so you see here that at each point x, y, we have a small line segment that represents the slope at a point. So we don't have a scale on this graph, so we're just kind of going to estimate where some of our points are. So we have, let's see, what point can I find? Let's do -1, 3. That was a 45-degree tilt, so that would be somewhere around here. That would be the point -1, 3. And then we would see here our point 1, 1. That was also a 45-degree tilt too. So let's say that this would be our point 1, 1. We also had our point 0, 2 and -2, 2, and those are both zeros. So that would be at the point here. So that would be 0, 0, 2 would be right here. And then we had -2, 2. So that would probably be somewhere in here. And you see here that we have a horizontal line that's formed at those 2 points, completely straight. So if we, I guess, were to zoom in a little bit more on this directional field, we would see that our arrows are going closer and closer to being horizontal. So step 3 now is to define critical points in equilibrium solutions. So an equilibrium point is a point where the derivative y prime equals 0, meaning the slope of the tangent line is flat, so it's horizontal. These are points where the solution curve doesn't change, it stays constant. So for our dE, y prime equals x times 2 minus y, we can see that for y prime equals 0, either x equals 0 or y equals 2. Hence, y equals 2 is the equilibrium solution. This means that when y equals 2, no matter what x is, the slope is 0 and the solution curve stays flat at this point. Critical points are points where the slope or derivative changes significantly, usually indicating an equilibrium or a transition in behavior. In this case, the critical point would be at y equals 2 because it's where the slope becomes 0. An equilibrium solution is the constant solution where y equals 2 for all values of x. So this solution corresponds to a horizontal line on the graph representing a stable behavior where the system doesn't change. Okay. Step 4, plotting the solution curve. So now that we've established the direction field and the equilibrium point, we can sketch the solution curve. So using the directional field as a guide, we can trace the solution starting at any initial condition. For example, if we start at y at 0 equals 1, so y of 0 equals 1, we would follow the upwards slope directional field until it levels out near y equals 2, because then that would be horizontal. So this would be the point y equals 2, not y equals 2, y equals 0, 1. That's the point. My apologies. And then we would just follow the upward sloping direction until we level off near y equals 2. Okay? If we start with the point 0, 3, so y of 0 equals 3, which is way up here, now we would follow a downward sloping direction field until it approaches y equals 2. Okay? So these solution curves show how the system evolves over time and how solutions tend to stabilize near the equilibrium point at y equals 2. Okay? Objective 3, identify an autonomous differential equation. An autonomous differential equation is a differential equation where the independent variable is not present. So in an autonomous DE, an equilibrium point is an equilibrium solution. For instance, dx dy equals 1 plus y squared, or dy dx equals the square root of y. Now let's consider the autonomous differential equation dy dt equals y times y minus 1 times y plus 2. Our first step is to find the equilibrium points. So remember, equilibrium points, also known as critical points, occur when dy dt equals 0, which means f of y equals 0. So we're going to set our function dy dt to 0. So f of y equals our dE, y times y minus 1 times y plus 2. And we're going to set it equal to 0, and we're going to solve for y. So that's going to be when all the factors are set to 0, because if any one of these factors equals 0, then our equation equals 0. So this would be y1 and y negative 2. So our values, y equals negative 2, y equals 0, and y equal 1 are all equilibrium points. Step 2 is going to be to determine the stability of each equilibrium point. So to classify each equilibrium point, we examine the sign of f of y around each point. This tells us whether nearby solutions move toward or away from the equilibrium point. So for y equals negative 2, we're going to check the sign of f of y on either side of y equals negative 2. So let's choose a point that has y less than negative 4. So we're going to choose a point for y that's less than negative 2. So we're going to choose -4. So f of -4, we would substitute into our function -4, -4 minus 1, -4 plus 2. And when we simplify this, we will get -40. Okay, so we chose a value that's less than -2, so we chose -4, substituted it into our function, and we got a value of -4. So that means f of y is less than 0, so it is negative. Okay, now we're going to choose a value for y that's greater than -2. So let's choose -1 and substitute that in to our function. No, that should be a plus. +2. So -1, -2, 1, now equal 2. Okay, so now our f of y is positive. So our f of y is greater than 0, so it is positive. Okay, so that means solutions move away from y equals -2 from both sides, making it a repeller or unstable point, an equilibrium point where nearby solutions move away from it. Okay, so we have -2, and when we choose a value less than -2, it continues to go negative, so it's moving away from -2. And then when we choose a value that's greater than -2, it's positive, so it's still moving away from -2. Okay, now let's check our other equilibrium point, 0, and we're going to do the same thing. We're going to find values that are greater and less than 0, substitute them in to figure out the sign of f of y. Okay, so for y less than 0, let's choose the point -1. And we know what f of -1 is because we have already solved it on the previous problem, and that came out to be 2. So we know f of y here is greater than 0, so that's going to be positive. Okay. Now for y greater than 0, let's choose another point that we haven't chosen before, and all the points that we have chosen are negative. And since our next equilibrium point is 1, we'll want to choose a point that's between 1 and 0. So let's just choose 0.5 or a half. Okay, so f of a half will equal a half times a half minus 1 times a half plus 2. So we'll have a half times negative a half times 2.5. So that will be 5 halves. So that will come out to be 4/8, so -5/8, which is -0.625, I believe. All right, so that is a negative value. So f of y is less than 0, so that's negative. Okay, so the solutions approach y equals 0 from both sides, making it an attractor or a stable point, an equilibrium point where nearby solutions move towards it. So we have 0, and when we choose a positive value, Is it positive first? No, negative, sorry. When we choose a negative value, all right, our f of y is positive, so it's wanting to pull closer to 0. When we choose a positive value, one that's greater than 0, our f of y is negative, so it's moving closer to 0. So our arrows are going towards 0. Okay? All right. Our last equilibrium point is y equals 1. So let's check the sign around f of y around y equals 0. So let's choose a y that's less than 1. So we chose 0.5 previously, so we can use that one again. So f of 1/2. And we got negative 0.625. So that means f of y is less than 0, so it's negative. Because it's negative. So now let's choose one that's greater than 1, and we've already chosen 2, so let's stick with 2. And so 2 times 2 minus 1, 2 plus 2, so that'll be 2 times 1 times 4, and that equals 8. So f of y is greater than 0, so that's positive. Okay, so this is similar to our first point. That was also a repeller. This is an unstable point because at this equilibrium point, our solutions are moving away from y equals 1 on both sides. Okay, so we found our three equilibrium. We found the stability of our 3 equilibrium points. Okay, so now in step number 3, we can create our phase portrait. And to complete the problem, we're now going to draw our phase portrait showing the behavior of the solutions around each equilibrium point. So here's the phase portrait for the differential equation dy dt equals y times y minus 1 times y plus 2. The equilibrium points are marked as follows. Excuse me. So we have 3 equilibrium points. We have 1, we have 0, and we have negative 2. Okay. So for 0, this is going to be our stability point, our attractor, because the nearby solutions move towards this point. So we're going to move towards 0. Okay, so that's my arrow. For moving towards 0, let me draw my arrow here. We're moving towards 0. Okay, making it a stable point. Now we have 2 unstable points at y equals negative 2 and y equals 1 because our solutions are moving away from those points. So they're moving in the opposite direction. And then this one as well, up here at the top. Okay, and that is our phase portrait for our dE dy dt equals y times y minus 1 times y plus 2. Okay, so these are for our 3 equilibrium points. Now, a critical point or equilibrium point that's neither purely an attractor, so a stable point, nor a repeller, an unstable point, is called a semi-stable point. This occurs when solutions move toward the equilibrium point from one side, but away from it on the other side. So I'll draw an example of what that could look like. So we have one side that's moving towards our critical point, And then on the other side, it's moving away from our critical point. And in this case, this would be considered a semi-stable point. Okay. This visualization helps us illustrate the behavior of solutions in the neighborhood of each equilibrium point. So this is our directional field for our DE problem that we've been working on. As you see here, we have an equilibrium point right here. Okay, and so this would be considered y equals 1. Then we have another one right here. This would be y equals 0. And then we have another one right here. This would be y equals -2. Notice in between each one of these critical points, the direction of our fields. Okay, so here we have the solutions moving away. Here we have the solutions moving away from 1, but towards 0. Here we have the solutions moving toward 0, but away from -2. And then here we have the solutions moving away from -2. So it's showing what the solutions are doing in each segment of our directional fields graph here. Okay, so that's how we can use phase shifts to show us what the solutions are doing between our critical points and equilibrium points. All right. All right, that concludes the section. Enjoy.